Good morning, everyone. My name is Howard. I'm from the University of Toronto Turbulence Research Lab, and today I'm going to talk a little bit about synthetic jet actuators for flow control. So, start with a bit of a background and motivation. So, the underlying physics that we're trying to combat is flow separation. Happens when there's a adverse pressure gradient on a flow surface. When we suffer from excessive flow separation and airfoil, it leads to stalling, and we lose a lot of the lift and suffer from increased drag, which is quite not ideal. One of the ways that we can go around is by applying active flow control. And at our lab, we apply a device known as the synthetic jet actuators, SJA, as a form of active flow control. Now, the way SJA works, they're kind of similar to human lungs. They alternate between ingestion and expulsion cycle. During ingestion, the cavity increase kind of draws air in, and during expulsion, the cavity decreases or volume. The cavity decreases and kind of squeezes the air out. Under the correct condition, we form a synthetic jet or a vortex ring. Now, the way to apply these is that we should have an area of them close to the leading edge of the airfoil. You should just upstream of the baseline separation point. This could also be done with a slot base or other type of SJAs. Here are some smoke wire visualization from the lab in the past where it was done with a slot-based SJA. I can see that with adequate flow control, we're able to suppress separation. There's a lot, or the boundary layers or the streamlines a lot closer to the airfoil surface. The size of the wick also significantly reduced, especially in terms of height. So we're going to start with the experimental side of things. So experiments were done at the University of Toronto Turbulence Research Lab. Wind tunnel, it's a closed wind tunnel, primarily looking into a NACA 25 airfoil. The friction velocity for this set of experiments were conducted at 5 meters per second with a turbulence intensity of 1%. This gives us a Reynolds number of 10 to the 5, and we're fixing the angle of attack alpha at 10 degrees. For this Reynolds number, we're expecting a laminar separation, and then the flow transitions to turbulent. So on the lower left is a rendering of the airfoil used in the wind tunnel. So we actually have two rows of SJAs. However, the second row is not activated. Only the first row is actuated. And each row have 12 SJAs. For the experiments we're presenting, we cover a range of blowing ratio from 0.5 to 3.8, and at two forcing frequency, F plus of 1.1 and 11. This translates to 20 and 200 hertz. All right. The lower right, we have a rectangular box that highlights where the SJs are embedded, basically pretty close to the leading edge, LE. So we're going to start the results off with some symmetry plane or mid-span smoke wire visualization. On the left of subplot A, we have the baseline case. We can see the flow is fully separated, and the little yellow arrow points to the wick shedding. Now, on the middle and the right, they're both actuated cases, both conducted with blowing ratio of 3.8. The middle one has a lower actuated frequency, whereas the subplot on the right, subplot C, has a higher actuation frequency. We can see that both of the actuated case were able to suppress flow separation, bring the streamlines a lot closer to the airfoil surface. And the wick size are actually sort of similar. However, at the higher forcing frequency case of the wick, the structures in the wick is actually a lot more finer. This actually translates to giving us a more steady flow overall compared to the lower actuation frequency case. Now, so these are long-time exposure photography. So taken downstream, or the camera is situated downstream of the airfoil within the air tunnel itself. The reflection at the bottom of the picture, the green white line, that's actually the reflection from the trailing edge of the airfoil. These are taken at exposure over the course of 1/4 to 1/10 of a second, which roughly translates to 3 convection cycle. So start at the subplot A, the blowing ratio of 0.47. we can actually somehow see some effect, or the SGAs were able to partially suppress flow separation. However, it kind of tilts towards right, and then the effect isn't very good. As we increase that to 1.5, we're able to suppress flow separation, especially towards the mid-span. As we further increase the blurring ratio, since we already suppressed the flow separations, the line itself, the streamlines doesn't get any closer. However, we do have better span-wise control authority, especially in terms of stability. Now, so these are top-down, smart wire visualization. LE is trailing edge, TE is leading. Sorry, LE is leading edge, and TE is trailing edge. So on the left of the baseline case, the flow isn't very exciting. It's nominally two-dimensional. When you have laminar separation, then it transitions to turbulence. Now, if we look at a subplot B, that's a lower actuation frequency case. So the frame we're looking at is focused on the actuated case, but then if you move further away or closer to the sidewalls of the wind tunnel, the span of the airfoil is actually not actuated, and the effect or the non-actuated zone is still separated, and it kind of causes this contraction, even that invades into our actuated zone. The yellow arrow kind of points at the contraction, and you can actually track them as they convect downstream if you have a series of instantaneous results. And so we can also observe something very similar for the high actuation frequency case. However, the contractions are less aggressive, but then at a higher frequency. Something else that we also observed in the high actuation frequency case is that we see what seems to be the cross-section of a tilted vortex ring. Now, this is very remarkable. We're seeing it remarkable because we're seeing this, observing this basically close to the trailing edge. This is basically almost like 300 diameter downstream of the jet slot. It's very high survivability. However, we did not observe that in the lower actuation frequency case. Now, if we look at the longer time exposure photography, again, top-down view in a baseline case, not very exciting, nominally two-dimensional flow. Both of the actuated cases actually look very similar in terms of the profile. The high actuation frequency case give us a slightly more well-defined profile, but both of them seem quite similar. This kind of tells us that even though the instantaneous flow changes quite significantly with the increase of actuation frequency, the mean flow doesn't seem to be impacted significantly. So we're going to move on to the numerical side of things. The simulations were conducted or ran in OpenFOAM with the Lambda-Sharman K-epsilon model. This is based on a standard K-epsilon model, but with damping functions employed, so giving us a little bit better results close to the wall. We've decided to attach the circular SGA into a duct crossflow rather than on an airfoil for two reasons. First, we're really trying to analyze the fundamental physics and especially the structures of the SGA without added complexity of other crossflow. And second, for the Reynolds number of the airfoil that we're working with, we have a laminar separation and the transitions to turbulence. We're not very satisfied with the URAN's results, and therefore we've decided to attach it and going with a duct crossflow instead. However, to ensure it's still comparable with the experimental flow, we gave it a very short development length, resulting in a very thin boundary layer. We're talking several millimeters, similar to what you expect on an airfoil right before separation. For the SGAs, we've gone with an analytical solution for the profile. This is based on the Wormsley solution approach, and it gives us a lot of control over the SGA effect. We outlined 4 cases from 120 Hertz to 850 Hertz. For reference, case B would be closest to the SGAs done on the airfoil and the experiment side of things at 200 Hertz. However, we've decided to increase the blurring ratio from 3.8 in the experiments to 4.8 for the numerical side of things. since URANS is known to be a little bit overly diffusive, so we're trying to compensate for that a little bit. So starting the result section for the numerical work with 3D instantaneous Q criterion contours. So the D here for the axes, that basically a slot diameter of the SJA, and it's used to normalize the streamwise, spanwise, and transverse distances. Here I've also attached an additional set of additional ticks in the spanwise direction, but basically most of the structures are confined to a plus minus 5 D direction in the spanwise direction. So let's start with the lowest actuation frequency case of 120 Hertz. Jet column form a tilted vortex ring, pretty classic. As we go into 200 Hertz, we can still faintly see the vortex ring. However, their orientation is more distorted, and then they're also like a smaller, and it seems to be more unsteady. Let's move on to 425 Hertz. However, we no longer observe distinct vortex ring. Instead, the structure seems to be a column or like a train. Yeah, it seems to be more connected together. Something else that we're also very interested in is the near-wall vortices. They sort of look like a arrowhead or like a double-sided fish hook. These are very close to the wall, usually 1 to 2 millimeter, and depending on your slot diameter, we might be looking at 1D. Very close to the wall, quite hard to observe experimentally. These are important since they directly allows us to suppress fold separation, as we'll see more in their boundary layer profile later. However, as the actuation frequency increases, it seems like the near-wall vortices, the shape itself doesn't change too much, but they get more compact in both streamwise and spanwise direction. Finally, if we look at the 850 Hertz case on the far right, we ran into the bane of URANS, which is overlamerization. The SJ boundary conditions were applied and functioning correctly. We have very high frequency jets coming out. However, the jet column or the flow relamerized shortly afterwards. So we have a snapshot of the isometric view on the lower left as reference, but we'll primarily be focusing on the side view XY plane and the frontal view YZ plane here. And so case A would be the lowest frequency case of 120 Hertz, and in case D at the bottom would be the highest frequency at 850 Hertz. So starting from the side view of XY plane, saw that as you increase the actuation frequency, actually decreases the jet penetration. Now, the boundary condition for the SJ gave us enormous amount of control. So we're actually exerting the same momentum per second into the crossflow across all cases. However, that's only momentum per second. So as you increase the actuation frequency, the period decreases. Therefore, the momentum per cycle actually also decreases. And therefore, we believe this is the reason why the decrease of the jet penetration as we increase the frequency. Something else we also saw in case C, the 425 Hertz case, we saw these tail-like structures. They kind of resemble the hairpin vortex legs from the side. However, here we only have one tail compared to the pair of legs of the hairpin vortex, and here it also tilts towards the downstream direction. And we move forward to the frontal view of a YZ plane. The effect of the reduction of the jet penetration becomes even more obvious. And we also observe that primarily the structures are combined to 5 and, well, plus minus 5 in the spanwise direction, or plus minus 5D, plus 6 minus 6, it being very generous. And especially for the newer structures, we're looking at spanwise coverage of maybe plus 2 minus 2D in each direction. And if we move on to the case D, the highest frequency case where it'll ramerize, it kind of broke the trend and the penetration increases significantly. And on the right in the frontal view, we also observe quite a bit of non-symmetry. The jet column kind of tilts towards one side quite significantly. Between the ramerization and the non-symmetry of the results, we're not very confident on this. We suggest using at least DES and preferably LES for looking at higher frequency actuation to avoid relamerization. So there's some time average boundary layer profile on the left. So these are basically plotted on the symmetry plane. The first one is plotted 5 diameter downstream of the jet slot, and the second one is plotted at 50 diameter downstream of the jet slot. So if we start with the one closer to jet slot on the left, we actually saw all the actuated cases were able to increase the near wall momentum quite significantly compared to the baseline case, which is in the solid line and teal. Now, this is actually really good since this is the increase of near wall momentum is what allows the SGA to suppress separation on a ramp and on airfoils. The profile between the actuated case, at least near wall, also seemed quite similar, irrelevant of the actuation frequency. However, if we move further away at the 50D, saw that their higher frequency case of 425 Hertz actually started having a deficit region compared to the other actuated case or even the baseline case. We believe this is a result of the tail-like structures at that frequency. And if we look at some time average skin friction coefficient contours, so these are plotted based on a time average streamwise watershed stress. For 120 Hertz and 200 Hertz, we had one peak at the symmetry plane. However, as we go up to 425 Hertz, we have two peaks. This again kind of resembles what we see on a hairpin vortex. However, we're not observing a hairpin vortex at 425 Hertz, just the tail-like structure. But it seems like the tail-like structures were able, or resulted in a slight change of the profile close to the wall. However, this doesn't seem to affect the magnitude of the near wall flow significantly. So how does the numerical side of things tie in with the experiment, right? Let's take a step back. If we look at the microblowers SJAs used on the airfoil, the slot diameter is 0.8 millimeter. The cavity is 20 millimeter, which translates to roughly 25D. And then if you look at the way they mounted on the airfoil, there's a 5 millimeter clearance. So a jet-to-jet distance of basically 35D, or slightly over that actually. However, the area of SJ is still able to function similar to a slot-based SJ, where provided a span-wise control section that's performing pretty well as a coherent front near the mid-span. So it's tempting to assume, oh, we have jet-to-jet interactions, so the different SJAs are working together, the structures are suppressing the flow separation, forming a coherent front similar to slot-based SJA. However, if you look at the numerical results, we are very confident that there are no jet-to-jet interactions in terms of structures. Again, each of the jet are basically mounted over 35 diameter apart. So there will not be direct jet-to-jet interaction in a nominally two-dimensional cross-flow. So just a quick recap. We conducted a series of experiments on an NACA-25 airfoil. We looked at high and low actuation frequency. We concluded that high actuation frequency and higher blurring ratio give us the best effect in terms of stability and span-wise control authority. On the numerical side, we conducted simulations on a single circular SJA in duct cross-flow. We fixed the blurring ratio and then looked at it by adjusting the actuation frequency. We saw that higher actuation frequency resulted in less jet penetration of the jet column. It also seemed to affect the profile of the near wall flow, but not as much, doesn't seem to impact the magnitude significantly. Thank you for listening.